Alright, so I'm going to do the first 10 of the indefinite integrals. There's 20 indefinite and 20 definite. So I'll do the first 10, these indefinite integrals that don't have limits. These are just finding antiderivatives. That's what this is. Whenever you see an indefinite integral, it says, or what you're supposed to do is just find the antiderivative. With definite integrals, finding the antiderivatives the first part, but then you have to evaluate it at the limits, that antiderivative. So I'll do kind of both sets. They're pretty similar. Finding the antiderivative is going to be the same in that step, but the definite integrals have kind of two main differences. So, and then just watch, like for the first 10 problems I do. Technically, it's the same thing every time, but there's little variations and problems and little things that you have to do that's a little different that you might not have thought of if you haven't seen before. Okay, so get started. Okay, so I'm gonna do the same thing every time generally. So look at like pay attention to like the steps that get repeated. Even though there might be little differences in the problems. Okay, first thing is try to identify what U is, and there'll be kind of two ways. Mostly U will be inside of some other function, kind of like when you're looking at when you're doing the chain rule, the function on the inside. That's almost always what you make U. And then just take a little thought of, okay, if I make this thing U, is du multiplied on the outside, and so this one's perfect. If we make x squared plus 3u, the derivative is 2x dx, and that's on the outside, so that kind of confirms what will make u. Okay, so let's make u x squared plus 3, and then du will be 2x dx. Alright, and then especially at the beginning when you're doing these, really try to see how you're just substituting, right? So now this thing in here, so now when we'll rewrite this in terms of u. Okay, so it's going to be the same integral, it's going to have the same answer, but it'll just be in terms of u, or same antiderivative. So yeah, so just be careful. So according to this, u is x cubed plus 3, x squared plus 3. So since we have an x squared plus 3 here, we can replace that with a u. Okay, here, sorry I made a mistake, so I don't know if this is gonna edit's gonna make sense, but okay, so now we substitute. So now this x squared plus 3 is u. So we'll replace this with u, so this will become a u cubed. And then this 2x dx, that's multiplied on the outside here, is we're going to replace, substitute with du. So this will be just u cubed times du. So let me write that. Okay, next step, after you get everything in terms of u, right? Just u's and du's instead of x's and dx. Okay, next thing is to actually integrate it, find the antiderivative. And so for this one, we'll do power rule. So anytime you have a variable to an exponent, just like with derivatives, there's the kind of opposite power rule for integrals or antiderivatives, which is you add 1 to the exponent and then divide by that new exponent. So if you add 1, u to the 4th, and then divide by 4. Okay, so next step, the last step, is to substitute back in. It started off in x's, we got it in terms of u, but now we have to put it back in terms of x. This U-substitution is kind of an intermediate step to make things simpler, right? This looks complicated, this much simpler. Take the antiderivative, but now we got to bring the x's back. So this is u to the 4th, so we'll replace that u with what we made u originally. Alright, that's it. Okay, so I'm not going to do it for all of them, but I'm going to take the derivative just to check and see that it doesn't take that much time. Okay, so now we're going to take the derivative of this. So when we take derivative, whatever this constant is, it'll go away when we take derivative. So we'll just focus on this part. So we take derivative. First off, this dividing by 4 is the same thing as multiplying by a fourth. So I'll kind of pull that out. And then when we take the derivative of the rest, this top part, we'll just do power rule and chain rule. So power rule with that 4. Keep that inside the same to the third. And then multiply by the derivative on the outside, doing the chain rule. So derivative of x squared plus 3 is 2x. Okay, then we simplify, and then I'll write the 2x out front. And then let's see if that's the same as the original. Yeah, perfect. Right, same as that. Yeah, so I just kind of checked our work. Okay, next one. So some of these are tricky. Some you have to rewrite before you can even do U-substitution. So even if you wouldn't have thought of this, the whole point of doing these problems is to find situations that you wouldn't have thought of, but now that you've seen it, then you will be able to do it for similar situations. Okay. So here, let's rewrite this. Okay. So you should kind of notice that this is looks like an inverse sine type derivative. And so if you think about it, if we make this 2xu, this will be 1 over square root of 1 minus u squared, which is exactly the derivative of sine inverse. But when we take derivative of 2x, that's 2, so we'll have a little constant that we'll have to make an adjustment for. Okay. Oops. All right, so let's do our U-substitution step. Sorry. Okay. So we'll make u 2x, the thing on the inside. So du will be 2 dx. And then we can even go one step further. Here there's no 2 dx, there's a 1 dx. So if we divide by both sides by 2 or multiply both sides by a half, we get that. And then now we can, for this dx, we can substitute it exactly for 1/2 du. Okay, so let's do our substitution. Okay, so this dx is really kind of in the top here. This dx could get multiplied in the top, so I'm going to put the 1/2 du in the top here. Okay, and then the bottom, 1 minus the 2x here, we said is u, so we'll replace that 2x with u to make this just 1 minus u squared. Okay, so I'm going to pull that 1/2 out first. But with practice, it doesn't matter. You can just do it all at once. Okay, now we take antiderivative. So this is just really 1/2 inverse sine of u plus c. All right, and then now we look at our u was 2x. So now we'll replace it. And that's it. Okay. I'm going to skip taking derivative of that one. Just don't feel like it. Alright, next one. Okay, almost always if you're dealing with a trig function, there's exceptions, but If you're just dealing with just an actual trig function, not a trig function squared or something like that, almost always you're going to make the thing inside the trig function u, and that's what we'll do for this one. And we can even kind of plan it out. If we make u equal to, x over 2 is 1/2 x, then du is 1/2 dx, and then we can multiply by 2 both sides, so that, so 2 du is just dx. So that's perfect. And then this, so that means this dx will make 2 du, so that'll be gone, that'll be 2 du. And then this x over 2 will become u, and that's how we'll get everything in terms of u. So we'll get a u here, du here, so no more x's, only u's, which is maybe the main goal. Okay, so now we'll substitute cosine u times 2 du. Right, that became u, that became 2 du over here. Okay, again, with practice you'll pull the 2 out automatically instead of doing it in 2 steps like this, but we'll do it in 2 steps. Okay, integral of cosine, you got to be careful. Derivative of cosine is negative sign, but integral of cosine is just positive sign. Okay, and then now our u was 1/2 x, really x over 2. So now we'll replace that. And that's it. Okay, next one. Okay, so this should be something that you'd like just kind of notice, that if you make u the inside of this square root function, just take a second to take the derivative, right? You can see if you take derivative of this inside, it's going to be 4x plus 3, which is perfect. That's that exact outside. If this 3 was a 2 or a 4 or something, this problem might not be possible to integrate. So just even little changes make it not possible to integrate, but that means problems are going to be created that do work out, so. Okay, so now definitely we'll make u the thing underneath the square root. Immediately take the derivative of both sides. So derivative of 2x squared plus 3 is 4x plus 3. We'll put it in parentheses because whatever you take the derivative of, the whole thing gets multiplied by dx. So if you have things added or subtracted here, you'll have to put it in parentheses and then multiply by dx. Okay, so this one's nice. We don't have to change this because 4x cubed, or 4x plus 3 dx is exactly what's on the outside. And then this on the inside is exactly u. So now we can just substitute. So this is really just square root of u du. So look how much that's simplified. Again, with practice, you could do this without U-substitution actually, but you'd have to be a little more careful. All right, so I'm going to rewrite this just like with derivatives. You have to rewrite roots as fractional exponents. Okay, and then we can do the power rule. Anytime you have a variable to a constant exponent, you can do power rule, except for if the exponent's -1. It doesn't matter if the fraction is positive, negative, fractions, pi, doesn't matter. Any kind of number that's not -1 as an exponent, you can use the power rule for integrals. Okay, power rule for integrals is add 1 to the exponent. And then technically you divide by the new exponent, so we'll divide by 3/2, but kind of good to just do this automatically. If this is a fraction, this exponent, just multiply by reciprocal, because you're going to do that anyways, right? Whenever you divide by a fraction, you just multiply by reciprocal. So I think better to just do that automatically. All right, and then we'll after you take the antiderivative, same step every time, just substitute for whatever u was. And that's your answer. Okay, and the answer, this answer might be written a different way. So it could have been like that, same thing. Okay, next one. Okay, this one, super tricky. Okay, if you've never seen this one before, this type, very hard to see what to do. Okay, first, definitely going to rewrite even this original integral. You know, anytime there's roots, you're gonna want to rewrite it anyways, but especially for one like this to see what's going on. And I'm gonna even rewrite. Actually, yeah, kind of always will rewrite both. Okay, so this is the integral. So I'm gonna rewrite this as x to the negative 1/2, and this is x to the 1/2. So, and I'm gonna kind of rearrange things. I'll write it sine of x to the 1/2 times x to the negative 1/2 dx. Okay, so just see that that's the same thing, just those roots have been written as fractional exponents. Okay, now, do you notice if you make this u, the derivative of x to the 1/2 is 1/2 x to the negative 1/2, which is perfect, right? X to the negative 1/2 here. So notice the derivative is 1/2 x to the negative 1/2, so that 1/2 that you get will cancel out later, just like we did with the first couple. Okay, so it's good, you know, it's whatever you make u, you know, you have to have the derivative of that multiplied on the outside, but it could differ by a constant that's multiplied. Okay, so we'll definitely make u x to the 1/2. Okay, always the next step after you make u something, almost always take derivative both sides. Okay, and then for this one, I'll multiply both sides by 2 to cancel out that half. So 2 du. Okay, so now u is x to the 1/2, so this will become u. And then x to the negative 1/2 dx is 2u, so this will become 2u, 2 du. Okay, I'm going to just pull the 2 out from the 2 du now. And I'm going to just do that automatically from now on. Alright, so after your substitution step, same thing every time. Take the antiderivative, so the 2 just gets rewritten. And then the integral of sine, remember you got to be careful. Derivative of sine is positive cosine, but integral of sine is negative cosine. Okay, and then I'll do two things here. I'll pull the negative out here, and then substitute what u was. So this u is x to the 1/2, but that's really root x, so I'll rewrite it as just root x. That's how you'll see it in the answer keys anyway. So okay, so that's the first 5. Notice it's the same. Notice the same steps every time. You know, some weirdness, right? Definite weirdness for this one to kind of see that x to that root x in the bottom is really x to the negative 1/2, which was the derivative of x to the half. So really hard to see that. This one, this inverse sine one up here, kind of hard to see that you had to rewrite that 4x squared, and that hard to see that would be helpful even. So, but now you know. So, okay, so let's go to the next 5. So almost any time you see a fraction, check to see if the derivative of the bottom is the top, maybe different by a constant. And that's what situation we have here. So x squared plus 3, derivative is 2x exactly. So whenever that happens, that means you're going to make u the bottom, and your answer is going to involve an ln. And if it seems complicated with practice, these become the easiest problems. Easy to spot because it's anytime there's a fraction, it's easy to spot because you just take the derivative of the bottom, notice it's the top, and then you know exactly what to do from there. Okay, so we'll do that, make u the bottom. Derivative is 2x dx, which is perfect, exactly what that is. So this will become du, and the bottom will become u. So we rewrite this. It's really just du over u. You could also think of it as, you could write it also like this, 1 over u du. Doesn't matter. Okay. So now take antiderivative. Antiderivative 1 over u is ln absolute value of u. Okay, we'll talk about why it's absolute value later. Really matters most when you're dealing with definite integrals, but true for these antiderivatives also. Okay, and then you plug back in for u, x squared plus 3, and that's it. Okay, and then one little just general math note. We could write this. Whoops. How come we don't need absolute value for this one? Most of the time we probably will, but for this one it actually didn't matter if we use absolute value or not, because this x squared plus 3 is always positive anyways, so really this absolute value is not really doing anything in this problem. So you could write this either way. Okay, next one. So another tricky one, I think. I think this is a super tricky one. Okay, so notice if we make u this whole thing, so notice it wouldn't be helpful to make u the inside of this ln. Most of the time you're probably going to do that, but then take another step. Let's say you make u this x plus 4, right? Then this will turn into ln of u over u, and then what? You have like a function ln over another function u, ln u over u, just dividing two functions. So it's like, where do you go from there? Okay, so this one's weird. Think about now if you make u this whole thing. So the derivative of ln x plus 4 is 1 over x plus 4 dx, which is really that. Right, the fact that x plus 4 is in the bottom, this is really 1 over x plus 4. Okay, so let's do that. And so here, I'll just do it and we'll see. So make u ln of x plus 4. Okay. And then when we substitute, notice that this here is really just these two things multiplied. Right? If you multiply this by this, you get the original integrand. And so really this is just u times du. That's all this integral is. Okay. Alright, so next step after writing it in terms of u is to actually integrate. Notice that's u to the first, so we'll do the power rule. Add 1 to the exponent, divide by the new exponent. Okay, then we'll substitute back for u. So this is like a weird little, so u is that whole ln x plus 4, and so that'll be squared now, and that's it. Okay, so a little weird situation, but okay, next one. Okay, a lot of times with fractions, we'll make u the bottom, but the only time you can make u the bottom is if the top is basically the bottom, the derivative of the bottom, maybe differing by a constant multiple. So that doesn't happen here, right? Derivative of this is 2x, but there's no x anywhere here. So can't make u the bottom. So you should see that this looks like the derivative of inverse tan. You know, if that was just a 1, this would be exactly inverse tan, and we wouldn't have to do U-substitution. Just that would be the answer. But not quite. So we'll look for see the technique for this one. Okay, so you know, this is something that you might not think of on your own, but now that you've seen it, hopefully you can get similar problems. So I'm going to pull out a 4 from the bottom, and with practice you'll do this a little differently, but I'll do this to show work. So I'll pull out a 4 from the bottom. Notice you get that. So notice when you pull out, and just in math in general, when you pull something out, you can pull anything out from anything. But whatever you pull out, the thing that goes inside the parentheses is just whatever you get when you divide the expression by the thing you pulled out. So technically we could pull a 3 out of this, or a 7 out of this, or a pi out of this. You know, typically it would just make the thing more complicated, so you wouldn't do it, but you can pull anything out of anything, because when you whatever you pull out, in this case a 4, you can easily get this by just dividing these by the thing you pulled out. Right, we pulled out a 4, so the thing so 4 divided by 4 is 1, and then x squared divided by 4 is there. Okay, so reason to do that though is now we can this is a 4 in the bottom, so it's really a 1/4 that's multiplied, so we can pull that out of the integral. And then this inside part, 1 plus x squared over 4, we'll do similar to one of the first problems we did, where this we can rewrite as x over 2, the whole thing squared. So we'll rewrite this will be 1 plus x over 2, the whole thing squared. Alright, now if we make this u, du is really just 1/2 dx, which is perfect. This is a 1 dx, so just differing by a constant. And then we'll have a 1 over u squared in the bottom, you know, a 1 over 1 plus u squared. And so that'll be inverse tan. Okay, so let's do the u substitution. U is going to be x over 2, which is really 1/2 x. Du is 1/2 dx. We'll multiply both sides by 2 to get that. Okay, now we'll do our substitution. So that x over 2, which is 1/2 x, we'll replace with u. And then that dx will replace with 2 du. I'll just kind of do it in steps. So this will be 1 over just u squared, since x over 2 is u. And then the dx is really 2 du. Okay, and then this 2 is a constant that's multiplied, so we can bring it out. And this will become 2/4, which is really just 1/2. And then now this becomes exactly just inverse tan. Okay, and then now we bring our u's back, so u is 1/2 x, or x over 2. Okay, and then you could rewrite it as just a single fraction. Okay, so you could write it like either one of those down there, down below. Okay, next one, pretty standard one. If we, inside the trig function, if we make that u, then derivative x squared is 2x, and here we have an x, which is perfect, just differs by a constant. Okay, so we're going to do that right away. Okay, and then here we have a 2x dx, but on the problem we only have an x dx, so we'll get rid of that 2 by multiplying by both sides by half. Okay, so now we'll do our substitution. This dx will become this x dx here will become a half du. So I'm just going to pull out the half right away. Okay. And then this really just ends up being tan u du. Alright. And then now, so still not easy. Still got to do a little bit more. So with practice, you'll just memorize. This might be a good one to memorize. Really, tan or cotan, kind of similar. So here we can rewrite tan as sine over cosine. So notice this is still in terms of u. Okay, but now we'll do another u substitution step. So we'll make u the bottom. And we can't make it u, so we'll have to make it some other variable. So we'll make it like v. So make the bottom equal to v. And then if we take the derivative, okay, and then we'll kind of just multiply both sides by a negative, because here we have a sine u du. But here we have to get rid of this negative. So just multiply both sides by a negative, so it'll be negative dv sine u du. Okay, and I don't really need these parentheses, but just to kind of see clearly that that's a u. But maybe unnecessary. Okay, so let's keep going. So now we'll rewrite the 1/2. Okay, and then this sine u du here is going to be negative dv. So this whole thing gets replaced with a negative dv, and then I'll just pull that negative out. So make that a negative half. So the sine u du is dv, and then the bottom cosine is v. Okay, so now this is something that we can directly find the antiderivative of. Dv over v, right, is really 1 over v dv. That's a v there. And that's ln. So this will be negative 1/2 ln absolute value of v. Okay, v was cosine u, but then u was x squared. So technically we could do this in 2 steps, but really this v would become cosine u, but the u here, according to our original step, was just x squared. And so So that'll be the final answer. Notice we brought the x's back, and that's what you have to do. If it starts off in x, it's got to end in x for these antiderivatives. Okay, next one, last antiderivative. Okay, so definitely we'll make this u, and the inside, so we'll have a secant squared u, and then we know the antiderivative of secant squared is tan, because derivative of tan is secant squared. So this one we'll just go right into making u. So x over 4 is 1/4 x. Dx. Okay, we don't have a 1/4 in the problem, we just have a dx, so we'll get rid of that 1/4 by multiplying by 4. And then now we can substitute. So I'll pull that 4 out. And this just becomes secant squared u du. Okay. And then integral of secant squared is tan. And then u is really x over 4. So now we'll substitute back. And that's it. Alright, so notice same thing every time ultimately, but little differences. Right, this one definitely different. We had to do U-substitution twice. Here we had another inverse trig function that was a little weird thing of factoring out something weird. Definitely this one was super tricky if you've never seen before. This ln one. First one's pretty standard. Last one's pretty standard, but so yeah, just some little tricky ones. Okay, so now we're doing the definite integrals. So try to notice the steps that are the same as the indefinite integrals, the one without limits, and then look at the differences. So definitely differences, especially at the end. So, the similarities you'll see are, we're going to find the antiderivative, just like we did for the indefinite integrals. We'll find the antiderivative of this inside. But here we have to evaluate that antiderivative at the limits in a certain way. And normally you'll just find the antiderivative, plug in the top and bottom, and subtract. But here we'll have an extra step of changing these limits. We'll see once we do the first problem. Okay, so definitely we'll make the inside this cubed function u, because derivative is 2 dt, and we have a dt here, so just differing by a constant multiple. So we'll just make u this right away. Okay, we just want a dt, not a 2 dt, so multiply both sides by half. Okay, and we'll substitute just like normal. I'll pull the half out. And then u is 2t plus 1, so that'll become u. So this will just be u cubed. And then dt becomes, this dt is half du, so that's half du. Okay, notice there's no limits here. Okay, so the thing to be careful of, this dt here tells you that t is the variable of this integral at the moment. Makes sense that there's t's here, but technically it doesn't have to be. This is what really tells you dt. That's the integral that that's the variable that this integral is in terms of t. So that means that these limits are t values. Sometimes they'll actually write on here, they'll write, t equals, t equals 1/2 or t equals 0. Sometimes they'll do that just to emphasize what variable those limits are in terms of, or equal. So yeah, so these original limits are t values. But here, this is in terms of u now, right? This du tells us this whole integral is everything's in terms of u. So we'll have to rewrite these limits from t values into u values. And we'll always do it with our original statement of what u was in terms of t. And you can just do the same thing every time. So just, this u is acting like a function of t. So we just plug in these t values into here, and we'll get it in terms of u now. And I'll even kind of write it this way. I'll do like u of the top limit and u of the bottom limit. Okay, so if you plug in a half into here, this is just 2 times a half is 1 plus 1 is 2, and that'll be our limit up here. And then if you plug in 0 into here, 0 plus 1 is 1, and that'll be our limit down there. Okay, when you do this step, almost always the top limit will start out bigger than the bottom limit. If it switches, sometimes it'll switch after you do this, get these limits in terms of u. Sometimes the bottom will be bigger than the top, but don't worry about it. You don't have to switch it. You can just leave it like that. Okay, so now just like in the other step, we'll take the antiderivative. Little differences. We'll start out with a bracket though. So antiderivative of u cubed, do the power rule for integrals, add 1 to the exponent, and divide by the new exponent. So one difference is there's no plus c for definite integrals, but instead we'll put the evaluation bar and then put those limits. Okay, another big difference is we're not going to substitute back in terms of x. And this function's in terms of u, these limits are in terms of u. There's no need to. We could, we could have actually kept these limits the same in terms of t, and then just substituted back, after you take the integral, we could have substituted to make this back in terms of t, and then just kept the original limits here, kept those there. But we don't have to. Better to not, actually. It just makes it easier. Okay, so to evaluate this integral here, this definite integral, we'll plug in the top, plug in the bottom for any u's, and then subtract. So plug in the top, you get 2 to the 4th over 4, minus, plug in the bottom, you get 1 to the 4th over 4. Okay, and then we'll just simplify this to a number. Okay, 2 to the 4th is 16. 1 to the 4th is just 1. Okay, so 16 over 4 minus 1 over 4 is 15 over 4. And then just, that'll become 15 over 8. Okay, and then that's it. So notice some similarities, right? Making u something and getting du, compensating if you have to multiply both sides, getting this antiderivative, or getting this all in terms of u, taking the antiderivative. So a lot of similar steps. Differences between this and indefinite integrals, no plus c, and you've got to evaluate whatever this is. You have to evaluate it at the limits. You don't have to get this back in terms of x ever. You can just keep it in terms of u and evaluate it in terms of u. Okay, so just to kind of see the broad differences between these. Okay, so this next one, okay, so this one, another little tricky one to see maybe, but here you have a tan and you have a secant squared. Obviously the tan is cubed, but anytime you see a tan and a secant squared, the derivative of tan is secant squared. So if you think about it, actually a couple things. Let's say you don't have to rewrite this, and you should see this without rewriting it, but I'm going to rewrite it just to make it super clear. You could rewrite tan cubed as tan psi cubed like that. It means the same thing. And then we'll put the secant squared psi d psi on the outside. Okay, so just to see clearly now, so when we make, if we make this tan psi u, derivative of tan is secant squared, so that's perfect. Okay, so let's do that. Okay, and then derivative be secant squared psi d psi. I think that's psi. Okay, so now we'll do our substitution step. This will become u. This whole thing will become du, so this simplifies a lot. Okay, so remember when you take the antiderivative, for these definite ones, we'll start off with a bracket, and then we'll substitute in the u cubed du, do the valuation bar, and then now we have to change these limits, right? This is in terms of u, but these original limits are in terms of psi in this case. Okay, so we'll use this original u statement to get our new limits here in terms of psi, or in terms of u, sorry. Okay, so we'll take u of the top limit, and we'll find u of the bottom limit. Okay, so tan of pi over 6 is root 3 over 3, and then tan of 0 is just 0. So this is our new limits, root 3 over 3 and 0. Okay, so now we will plug in the top limit. Oops. Oh, sorry. Now we'll take the antiderivative. I don't know why I said. Wait. Oh, I kind of made a mistake. Here, sorry. So we didn't even take the antiderivative yet. We just substituted. Okay, so you get bonus points if you notice that. Maybe. All right. So that's where these limits go first. Root 3 over 3 and 0. Okay. Okay, so now we'll take antiderivative. So do u to the 4th over 4, evaluated at root 3 over 3 and 0. Okay, so now just plug in the top limit. Okay, I'm going to write this as 1/4 just because it makes it easier. So this is really 1/4, and then we'll plug in the top limit. And then minus 1/4, plug in the bottom limit. Okay, and then now just simplify this to be a number. So that's just 0, so that'll go away. And then this will be 1/4. So if when you cube a fraction, or do a whole fraction to an exponent, you can just do the top and bottom to that exponent separately. So root 3 to the 4th is really root 3 squared squared. So root 3 squared is 3, and if you square that again, you get 9. So that'll be 9 over, and then this bottom 3 to the 4th is 81. So 9 over 81 is 1/9, and that's 1, so that'll be 1 over 36. Okay, so something to get used to. Whenever you see kind of a couple trig functions, try to see if like one is the derivative of the other. So just really, it's really common that that'll happen. So okay, next one, pretty standard. First thing always is to rewrite roots as fractional exponents. So let's do that first. Okay, so pretty standard. We'll make this inside u, and the derivative of this is negative 2x dx, and here we have an x dx, so it's perfect. Okay, Here we have a negative 2x dx, but here we only have an x dx, so we get rid of that negative 2 by multiplying by negative half. And then now we can substitute directly. Alright, so I'll pull that negative 1/2 out. And then this just becomes u to the 1/2 du. Okay, we'll get our limits. And just so you know, we could do that at any step. Right when we get this u statement, and maybe just check to see the du, we could change the limits right away. So there's no order for this. So plug in the top limit and the bottom limit. Okay, so if you plug in 1 into this, then you get 0. If you plug in 0 into this, you get 1. So these kind of flip-flop. And those will be our new limits. So notice this 1 became a 0, and this 0 became a 1. So notice it started off, the bigger one was in the top, but it ended up the bigger one was in the bottom. That just happened. So you don't have to switch it. You could switch it. You could switch these if you wanted, and then change that negative to a positive. Doesn't really matter. Doesn't matter to do it either way. Okay, so I'm just going to take the antiderivative right now. So antiderivative u to the 1/2 is u to the 3/2. Add 1. It's a fractional exponent. Just better to just multiply by reciprocal right away. Okay, and then just little things. You can, this constant, you can kind of just pull out of the whole thing. If you multiply these two constants, this will be negative 2. Actually, these 2's cancel. So that'll just be negative 1/3. Like that. And then you can do that. And then now you can just pull that constant out. Oops. That should be a 1 in the bottom. And then evaluate this. So plug in the top limit. So 0 to the 3/2 minus plug in the bottom limit. 1 to the 3/2. And then now we'll evaluate this. So that's just 0 minus 1, which is negative 1. And so that's just positive 1/3. Okay, how many have we done so far? 3? Okay, next one. Alright, another tricky one to see. So notice you've got an ln u, and you've got a u in the bottom, but having u in the bottom really means there's a 1. This is like a 1 over u. So I'm just going to rewrite this and see if this makes more sense. And another thing that's going to make this weird, here this original 1's in u, so typically we do U-substitution, where we'll get it in terms of u, but if it already starts out in terms of u, then we'll have to choose another variable. I'll choose v, I guess. That's what I think they usually do. Doesn't really matter. We could actually put x and get it back in terms of x, but I don't want it to. That might be more confusing to some people. But okay, so think about, make sure just algebra-wise that you can do this. You could rewrite this as, think about, you've got this ln u in the bottom, so that's like a ln u to the negative 1. Actually, no. We could write it like that, but maybe it's better to just write it as 1 over ln u, and then we could do this times, this is 1 over u, and then du, like that. Okay, so just notice that's the same thing so far. Now, if you make ln u v, we'll make this v, we'll do v substitution. So if we make this v, then the derivative is exactly this, right derivative of ln u is 1 over u du, which is multiplied on the outside, and that's what you want. So that's what we'll make v. dv is 1 over u du. Okay, so now when we substitute, so v is ln u, so this will become v down here. And then all of this, according to this, is dv. So this is 1 over u, or 1 over v dv. Okay, now we'll rewrite our limits. So we'll take v of the top, v of the bottom. Okay, so just plugging in, remember these are u, so these here are u values because this is in terms of u. So we'll plug them in for this u here to get it in terms of v. So ln of e cubed. Okay, ln of e cubed is e to the third is just 3. Ln of e to the 1 is just 1. So if you do ln of e to an exponent, you just get back that exponent. Okay, so those are our new limits. Okay, now we'll take antiderivative. So antiderivative of 1 over v is ln v, right? Antiderivative of 1 over x is ln x. So here we'll do this as ln, or the absolute value of v. Okay, plug in the top limit. Top limit, ln, we don't need the absolute value since we're plugging in numbers. Ln of the bottom limit. Alright, and then just so you know, ln of 1 is 0. So that just goes away, and our answer just is ln 3. Okay, next one, very straightforward. So make, just have a simple trig function like sine or cosine, and it's something other than just x or theta or whatever. This inside part will make u. So okay, u equals 3 theta, so du is 3 d theta. Okay, we don't have a 3 d theta, we just have a d theta, so times by a third. Okay, now we'll substitute. So that 3 theta will become u, and this d theta will become 1/3 du. So the third I'll pull out. Okay, we'll get our limits. So we'll do u of the top limit, u of the bottom limit. Okay, so plug in pi over 2, you get 3 pi over 2. Plug in 0, you get 0. Okay, so now take antiderivative cosine. Derivative cosine is negative sine. Antiderivative cosine is just positive sine. Okay, just a reminder, you don't have to put it back in terms of x because this is in terms of u, and we got these limits in terms of u. So everything we can just evaluate in terms of u. Okay, just little things. If you have a constant multiplied by the integral that you're about to, or the antiderivative that you're about to evaluate, then you need to put this in parentheses because this will be two things subtracted. So that constant has to get multiplied by the whole thing, both things that are being subtracted. Okay, so we'll just plug in the top limit minus plug in the bottom limit. Okay, and then sine of 3 pi over 2 is negative 1. Sine of 0, this goes away, that's 0. And so this is just 1/3 times -1, so that's just -1/3. All right. Okay, next one. So nice when you see a fraction. First thing I do is look at the bottom. If I take the derivative, is that basically the top, but maybe different by a constant? Yes. So make u the bottom. And we know our answer is going to involve ln. Okay, we have a 2x dx, but here we only have an x dx, so we'll get rid of that too. And then we'll substitute. Okay, I'll pull the half out. And we place this x dx with a half du. That half can get pulled out. And then this is just 1 over u du. Okay, get our limits. So u of the top limit, u of the bottom limit. So if you plug in 3 here, you get 9 minus 3, 6. Plug in, to find u of 2, plug in 2 here. We get 4 minus 3, which is 1. So those are our new limits. And then integral of 1 over u is ln absolute value of u. Okay, plug in the top limit, minus plug in the bottom limit. Remember, ln1 is 0. And so this is just 1/2 ln6. Okay, here are just little things with this. Remember the rule of exponents, where if you have like a times ln b, you can like make this thing outside the exponent. So this is just ln of b to the a. A lot of times they teach it the other way around. If the log has a exponent, the thing inside the log has an exponent, you can bring it out. But if it's out, you can bring it in also. So notice if you can, anything that's multiplied by a log, you can bring it in and make it the exponent of the argument. So we could do that here. This 1/2, we can make an exponent of 6. And that's really ln of root 6. So just in case you see, just in case you get an answer and you're like, you know, maybe it's multiple choice and this isn't one of the answer choices, just know that they'll do things like this when there's logs. They'll use those log properties to rewrite it. So, okay, next one. So same thing, fraction. Derivative of the bottom is actually the top exactly. This one's going to be easy. Okay, get our new limits. Okay, plug in 1 here, you get 4. Okay, plug in -2 here, you get 1. Those are our limits. Okay, the integral of 1 over u is ln absolute value of u. Okay, plug in the top, minus plug in the bottom. ln1 is 0. So this is just ln4. Okay, next one. Okay, so here we'll see, you know, we have a secant squared on the outside and a tan on the inside, so definitely we'll make u this whole thing. So if you make u 1 plus tan x, that if you take derivative, the 1 goes away, and the derivative of tan x is secant x, so perfect. Okay, so u is 1 plus tan x, so this is u to the fifth. And then du is secant squared x dx, so this is du. So u to the fifth du. Okay, we'll do our limits. U at the top, u at the bottom. Okay, so plug in pi over 4 for tan, so tan of pi over 4 is 1, plus 1 is 2. And then plug in 0 for x, tan 0 is 0, so 1 plus 0 is 1, so those are our new limits. Okay, integral of x to the fifth, x, oops, or u to the fifth is u to the 6 over 6. Okay, plug in the top limit, minus plug in the bottom limit. Okay, 2 to the 6 is 64. 1 to the 6 is just 1, so this will be 63 to the 6th. And then you could divide by 3 to simplify it, so it'll be 21 over 2. Okay, next one. This might be the first exponential. We'll see exponentials more than this. This is like almost the last problem, and we're just seeing exponentials. Yeah, so there'll be more exponentials usually. Okay, so almost always you'll make, if you have an exponential, write a constant to a variable exponent. Almost always you'll make the exponent u, and then just see if you make x cubed minus 1u, derivative is 3x squared, and here you have an x squared, so that's perfect. Okay, here we have a 3x squared dx, but in the problem we only have an x squared dx, so we got to get rid of that 3. Okay, so now we'll substitute. Okay, pull out the 1/3. Okay, so this whole thing is a third du, and this just becomes a u here, so this is u, e to the u du. Okay, and then we got to get our new limits, so u to the 1, u to the 0. Okay, so if you plug in 1 here, you get 0. If you plug in 0, you get negative 1. Those are our limits. Okay, integral of e to the u, same as the derivative of e to the u, which is just e to the u. The only function that if you take derivative or take antiderivative, you get back the same function. Okay, plug in the top limit, minus plug in the bottom limit. Okay, e to the 0, just like anything to the 0 is 1. And I don't know, we'll write this as 1 over e maybe, and leave it like that maybe. You could do more. You could distribute the 1/3. You could find a common denominator and then distribute the 1/3. I won't do too much but with this, but just to see, this might be how they write it. Okay. And all that is finding, 1 you could write as e over e. So e over e minus 1 over e is e minus 1 over e, and then just when you times a third by a fraction, that 3 just gets multiplied by the bottom. Okay, so either one of these could be the answer. You can see this one just by the looks of it, looks more simplified. So, you know, um, if it's a multiple choice, maybe they'll write it like that since it's more simplified. All right, last problem. Okay, so if we make the inside of this root u, derivative of 9 is 0, so derivative of 3w is 3dw, and that's perfect. The only thing on the outside is a dw, so that'll work. Okay, there's no 3 in the problem, so we'll get rid of it. Okay, we'll do a couple things here. We'll substitute. We'll pull out the third. And when we substitute, you know, technically this will be a root u, but I'll change it right away to a 1/2. Okay, get our limits. Okay, 7/3 times 3 is 7, plus 9 is 16. Okay, plug in 0 to the bottom. We get 9. Those are our new limits. Okay, antiderivative. Remember, it doesn't matter what this exponent is, except -1. But anything but -1, any number, fraction, positive, negative, e, pi, doesn't matter. Just add 1 to the exponent and divide by the new exponent. But when you divide by a fraction, you really multiply by the reciprocal. Okay, I'm gonna do an extra step where we multiply these constants. So this constant can get pulled out even from this step. You know, here we're at the step where we're just about to evaluate this integral at these limits. But even at this step, we can pull this constant out. Okay, and then now we can evaluate it by plugging in the top and bottom and subtracting. Okay, so that's going to be 2/9. Okay, so just a little algebra reminder. So when you have a fractional exponent, the bottom is like the root and the top is the power. So we'll take the square root of 16, which is 4, and then raise it to the third power, 4 to the third. 64. And the same thing here, the square root of 9 is 3, 3 to the third is 27. Okay, so 64 minus 27 is 37. Okay. Is that right? Yeah, I guess so. Okay, and then here we'll, you know, do just 2 times 37. And that should be the most simplified, over 9. Alright, so I did a bunch. So those last ones I did a lot quicker because it was so repetitive. Okay, but look at these 5. These last 5, even with me explaining, only took about 10 to 15 minutes. So you can see with practice, you could do these really can be quick. Not to say they have to be super quick or anything.